In this video, we will talk about dynamic optimal control and performance index. Performance index is another name for objective function or objective criterion. The example that we discussed in the previous videos is an example of steady state or static optimization. However, for MPC, we make use of dynamic model of the process. So, it gives rise to dynamic optimal control. Dynamic in a sense that the model of the process represents its dynamics or gives its dynamics, and also the control action acts on the process dynamics. Optimal in a sense that the future values of the process is utilized to make an optimal control problem, which is an optimization problem. Let us for simplicity use a simple block diagram of the process that shows its inputs, outputs, and the states. There could be many inputs, many outputs, and many states. Now, the process is a dynamic process. Now, how do you use the model of this process? We know that we can simulate the model of the process from any given starting time to a given end time if we know the initial value of the process at the start time. To make a dynamic optimal control, we simulate the model of the process from the current time to end time steps forward in time. Now, if we know the initial values of the process at any given time, let's say at k equals to 0, we can simulate this process n time step forward in time. Let's suppose the sampling time is dt. And we can calculate the dynamics at each time. Let's suppose the dynamic is something like this of the process. Now, by making use of these future values of the process, we will make an objective function. To give you an example of objective function, let me take an example of a setpoint tracking problem. Let us assume that we want to control the output of the process to a predefined setpoint values. So, we can formulate our objective function as a minimizing function that minimizes the difference between the actual output of the process and the setpoint. In this equation, we want to find the control input u that minimizes a cost function, j. J is an integral from 0 to infinity. Inside, we add two terms. The first term is the error vector, e of t, multiplied by the matrix Q, and then multiplied by e of t again. The second term is the control input vector, u of t, multiplied by the matrix R, and then multiplied by u of t again. Let's break down what this means for performance. The error e of t is the difference between the current system state and the desired state, usually 0. We want this error to be small and to go to 0 quickly. The integral adds up the error over time. A smaller area under the error curve means the system spent less time away from the goal, which is better performance. But state errors can be positive or negative. We don't want negative values to cancel out positive ones, so we square the errors using the quadratic form E transpose of t times q times e. This ensures the cost is always positive. Squaring also means larger errors are punished much more than smaller ones. This quadratic shape is very important. Think of a simple function like z equals x squared plus y squared. Its graph is a smooth bowl, which is convex. A convex function has one clear, global minimum. By designing our cost function j to be quadratic, we guarantee it has a single, well-defined minimum that we can actually find, even when our system dynamics are linear. Now, to control which errors matter more, we use the Q matrix. Q is a square matrix, usually diagonal, with positive values. Each value on the diagonal weights the importance of a corresponding state. To force a particular state to have very low error, we make its weight in the Q matrix very large. For states we care less about, we make the weight small. Q must be positive definite, meaning E transpose of t times q times e is always positive for any non-zero error. The second part, u transpose times or times u, penalizes control effort in the same quadratic way. The R matrix is also positive definite and typically diagonal. Large values in R mean we want to conserve that specific actuator, perhaps because it's expensive or uses limited fuel. We can visualize Q and R as parts of one larger block diagonal weighting matrix. While you could fill in the off-diagonal blocks to penalize cross products between states and inputs, we often keep things simple and set those to 0. So, our design focuses entirely on tuning Q and R. In summary, this formulation lets us precisely specify our goals. If performance is critical, like using reaction wheels on a satellite with solar power, we increase Q to demand very small errors. If actuator effort is costly, like using thrusters with finite fuel, we increase R to save energy, accepting a slightly slower response. The big question for the control designer is, given this clear trade-off, how do we choose the best values for Q and R to get the behavior we want from the system? Now, to calculate the process output, we need to simulate our system, or we need to simulate the dynamic model of the process. Thus, our constraints will be defined by the model of the process. Let us use linear model of the process. So our constraints will also be where this is the dynamic model of the process. Other processes can be the bounds on the decision variable. Let me also explain some of the variables or parameters that are in this equation or in this performance index. Qk is the weighting matrix for the error and Pk-1 is the weighting matrices for the control signals or the control inputs. The weighting matrix Qk should be greater than 0. However, the weighting matrix Pk could be 0 or greater than 0. Here we are taking K-1 index because the previous control input acts on the current output of the process. Or in other words, the output of the process is the outcome of the previous input or the input applied at the previous time state. Okay, now we have defined both our objective function. Let me remind that our objective function was to track this set point. And then in doing so, we also define different constraints that arise in the process, the model of the process and other constraints. Now that we have an optimization problem with objective and constraint, what we do is we solve this optimization problem. One more time, I would like to remind you that this optimization problem was formed by taking into account the dynamics of the system, from the current time to n time step ahead of the current time. Or in other words, this optimization problem is a dynamic optimization problem because to see the process behavior or dynamics or the outputs of the process from the current time to n time steps ahead in the future, we need to simulate the process from the current time to n time step forward, assuming that we know the initial state or the initial value at the current time. That is why the model of the process is being used. So it is a dynamic optimization problem. Okay. Now we solve this dynamic optimization problem. We will talk about how we can solve it later on in details. And then what do we get after solving this optimization problem? We get the best or the optimal values of U. And we get n number of optimal values of U. And we apply this n number of optimal values of U to the process. And when you apply the optimal solution, probably we will satisfy our objective of meeting the set points. So probably our controller would act in such a way that the set point is satisfied throughout the horizon from k equals to 1 to k equals to n. The horizon from k equals 1 to k equals n is also called the prediction horizon. And a prediction horizon is a parameter that the user has to define. It is called prediction because we are predicting the behavior of the plant using its model into the future from the current time. Now, thus to sum it up, let me again explain that this optimization problem is solved, and when we solve this optimization problem, we will get best or optimal values of U. And we get n number of best or optimal values of U, and when you apply this best or optimal values of U to the process, probably we will fulfill our objective or we will meet our goal, and our goal for this example was to track the set points. So, the output of this process as shown in this graph is the consequence of finding the optimal values of the control inputs. And it was found by solving this optimization problem. And this optimization problem was formulated by looking ahead of the current time. And by utilizing the dynamics of the process that happens ahead of time n time steps ahead. So, we predict its future behavior and try to control the process, or track the set point. Sometimes we also formulate the optimal control problem by using not the control input variables but by using the rate of change or deviation of the control inputs. We can then formulate our objective as follows. Here, instead of using U, we use the rate of change of control inputs. We denote it by delta U. The rate of change of control input is the difference between the current input and the previous time step input. This is also a way of formulating a dynamic optimal control problem. In addition, there can be also profit maximization problems or production maximization problems. However, in this course, we will not focus so much on profit maximization and production maximization problems. Okay, to sum it up, now let us write our optimal control problem or the dynamic optimal control problem where we define both our objectives and constraints. It was something like this. And I'm taking the example of set point tracking. This is a dynamic optimal control problem. However, this problem is a quadratic optimization problem. We know that. Because the objective is quadratic in nature, E has a power raised to 2 and U also has a power raised to 2. Model is linear, the constraints are linear. So all of the constraints are linear constraints. So objective function with quadratic nature and linear constraints forms a QP problem. However, the standard QP problem is as follows. Here Z is the vector that contains the variables that we would like to optimize, and this is a quadratic objective, and here we have linear equality constraint, linear inequality constraints, and the bounds. So before we can solve the dynamic optimal control problem, we have to change the dynamic optimal control problem of this form into standard quadratic programming problem of this form. In the next video, we will explain as to how we can do this transformation from dynamic optimal control problem, which could be a general QP problem with respect to control point of view, to a standard QP problem using efficient methods. The standard QP problems are generally the structure that are available in the solvers. So we have to express this structure into this structure if we want to utilize the solvers to solve the problem, and that transformation or formulation is explained in detail in the next video. If you enjoyed this video, give it a thumbs up, it really helps support the channel. Subscribe for more content on MPC, and don't forget to hit the bell so you never miss an upload. Drop your thoughts in the comments below, I read every single one. What should I cover next?